Once again, welcome to chemistry classes by Vijay Kumar Sethi. Class 11th chemistry. We were discussing unit 11, the p block elements, and in this video we will discuss about chemical properties of group 13 elements. First we'll discuss about oxidation state and trends in chemical reactivity. Due to small size of boron, the sum of its first three ionization enthalpies is very high. Therefore, it forms only covalent compounds. The sum of the first three ionization enthalpies of aluminium considerably decreases and is therefore able to form Al3 plus ions. In fact, aluminium is a highly electropositive metal. Due to inert pair effect in gallium, indium and thallium, both +1 and +3 oxidation states are observed. The relative stability of +1 oxidation state increases down the group. It means in the aluminium, +3 state is most stable while +1 state is least stable. While in case of thallium, +1 state is most stable and +3 state is least stable. In thallium, +1 oxidation state is predominant, whereas the +3 oxidation state is highly oxidizing in character. It means Tl3 plus will easily convert into Tl plus. Okay, so Tl3 plus is oxidizing in nature. The compounds in +1 oxidation state are more ionic than those in +3 oxidation state. In trivalent state, the number of electrons around the central atom in a molecule of the compounds of these elements, for example, boron in BF3, will be only 6. Such electron deficient molecules have tendency to accept a pair of electrons to achieve stable electronic configuration and thus behave as Lewis acids. Simply we can say group 13 elements in their trivalent state act as Lewis acids because they are electron deficient. The tendency to behave as Lewis acid decreases with the increase in the size down the group. BCl3 easily accepts a lone pair of electrons from ammonia to form BCl3 dot NH3 addition compound. Reaction can be represented like this. This BCl3, this is a planar molecule. This NH3, in NH3 nitrogen has one lone pair of electron and boron has one empty p orbital. Okay, this is electron deficient. So this lone pair of electron is donated to this B and this is tetrahedral. Now again, if you see the change in hybrid state, in this case boron is sp2 hybridized, but here boron becomes sp3 hybrid. Clear? AlCl3 achieves stability by forming a dimer. This is the dimer of aluminium chloride. In trivalent state, most of the compounds being covalent are hydrolysed in water. For example, the trichlorides on hydrolysis in water form tetrahedral species like this. MOH4 minus. This is tetrahedral. The hybridization state of element M is sp3. Aluminium chloride in acidified aqueous solution forms octahedral AlH2O6 3 plus ion. In this complex ion, the 3d orbitals of aluminium are involved and the hybridization state of aluminium is sp3d2. Now one problem 11.1. Standard electrode potential values, that is E naught for Al3 plus oblique Al is minus 1.66 volt and that of Tl3 plus oblique Tl is plus 1.26 volt. Predict about the formation of M3 plus ion in solution and compare the electropositive character of the two metals. Okay. Actually, these electrode potential values are the reduction values. Okay, standard electrode potential values are
represented reduction process. So you can say that is this Al3 plus will gain these 3 electron and converting into Al, and for this electrode potential is this minus 1.66 volt. In the same way, if you compare for thallium, then Tl3 plus will gain the electron and convert into Tl. Okay, this 1.26 volt standard electrode potential for this process. Now we can say if higher the value of standard electrode potential, it means this ion will easily convert into this one. Now if we compare these values, for aluminium this is in negative and for this thallium this is in positive. So we can say this aluminium will not easily convert into Al. Okay, so we can say E naught values for two half cell reactions suggest that aluminium has high tendency to make Al3 plus ions. Clear? Because for this value is negative. Whereas Tl3 plus is not only unstable in solution but is a powerful oxidizing agent. Thus, Tl plus is more stable in solution than Tl3 plus. Aluminium being able to form plus 3 ions easily is more electropositive than thallium. Is that clear? Now, reactivity towards air. Boron is unreactive in crystalline form. Aluminium forms a very thin oxide layer on the surface which protects the metal from further attack. That is, Al2O3 is passive in nature. But amorphous boron and aluminium metal on heating in air form B2O3 and Al2O3 respectively. With nitrogen at high temperature, they form nitrides. See this element react with the oxygen, it will form E2O3, and when react with the nitrogen, they form En, nitride. Now if we compare the nature of these oxides, then B2O3 is acidic, Al2O3 and Ga2O3 are amphoteric, Ln2O3 and Tl2O3 are basic in nature. Reactivity towards acids and alkalis. Boron does not react with acids and alkalis even at moderate temperature. Aluminium dissolves in mineral acids and aqueous alkalis and thus shows amphoteric character. Aluminium dissolves in dilute HCl and liberates hydrogen gas, and reaction can be represented like this. 2Al plus 6HCl, it will form AlCl3, and in the aqueous solution, AlCl3 will exist like this, Al3 plus and Cl minus, along with the liberation of hydrogen gas. However, concentrated nitric acid renders aluminium passive by forming a protective oxide layer on the surface. Aluminium also reacts with aqueous alkali and liberates dihydrogen. Reaction can be represented like this. 2Al plus 2NaOH plus 6H2O convert into 2NaAlOH4. Its name is sodium tetrahydroxoaluminate third, and hydrogen gas is liberated. Reactivity towards halogens. These elements react with halogens to form trihalides except TlI3. Reaction is 2E plus 3x2 converting into 2EX3 where X may be F, Cl, Br and I. Now another question, problem 11.2. White fumes appear around the bottle of anhydrous aluminum chloride. Give reason. Answer is anhydrous aluminum chloride is partially hydrolyzed with atmospheric moisture to liberate HCl gas, and moist HCl appears white in color. Now, important trends and anomalous properties of boron. The trichlorides, bromides and iodides of all these elements being covalent in nature are hydrolyzed in water. Species like tetrahedral MOH4- and octahedral MH2O6 3+, except in boron, exist in aqueous medium.
The monomeric trihalides, being electron deficient, are strong Lewis acids. Boron trifluoride easily react with Lewis bases such as NH3 to complete octet around boron. We already discussed this reaction. This is like in this boron is electron deficient, and this nitrogen has one lone pair of electron. This electron pair is donated to this boron, forming this addition compound. It is due to the absence of d orbitals that maximum covalency of boron is 4. Since the d orbitals are available with aluminium and other elements, the maximum covalency can be expected beyond 4. Most of the other metal halides, for example AlCl3, are dimerised. Dimerised means two molecules will combine and make one molecule through halogen breezing. For example, Al2Cl6, see this. This is the dimer of AlCl3. The metal species completes its octet by accepting electron pair from halogen in these halogen breezed molecules. This halogen breeze,
this chlorine has a 3 lone pair of electron, and this 1 lone pair of electron is donated to this aluminum. In this way, octet of this aluminum is also completed. In the same way, octet of this aluminum is also completed. Now, problem 11.3. Boron is unable to form BF63- ion. Explain. Due to non-availability of d orbitals, boron is unable to expand its octet. Therefore, the maximum covalency of boron cannot exceed 4. Thank you.